All right, let's take a look at our eighth example problem from chapter 6. So, a boiler of a Rankine power cycle absorbs 1000 kilowatts of heat from a furnace at 700 degrees C. The power plant rejects 850 kilowatts of heat in a river at 25 degrees C. What is the efficiency of the cycle? What is the rate of entropy generation? And what is the maximum possible power that could be produced by a plant given the temperatures of the furnace and the river? All right, sounds fun. So let's start with a picture. Let's label what we have and let's go from there. Okay, so if I try and draw my Rankine cycle. Okay, so I'm going to have my boiler, right, which receives heat. So this is what's going to receive heat from my hotter body. Okay, then from my boiler, I'm going to go to my turbine. Okay, sorry, I'm just going to draw everything as a box, given my artistic abilities. Okay, so then that's going to go to my turbine, and my turbine's going to produce work. So this is where I'll get some work out, and let me label it, say, WT for my turbine. Then for my turbine, we'll go to my condenser. Okay, and in my condenser, that's where I'm going to reject heat to my cooler body. So I'll label this one as TC. And then from our condenser, we go to our pump. Okay, and so our pump's going to take some work in. And so I'll label that WP. And then from our pump, we go back to our boiler to complete our cycle. So I'll label this stream 1, stream 2, 3, and 4. All right, and so now the key is this is a cycle, all right? And so, if I take my plant, right, as my system, all right, the change in internal energy, the change in enthalpy, the change in entropy, right, if I start at, point 1 here and end at point 1 is going to be 0, all right, because enthalpy, entropy, internal energy, they're all state functions. Okay. All right, so let's take this one at a time. So we've got our picture. Now let's label things. So we're told that we absorb 1,000 kilowatts of heat from the furnace. So our furnace, TH, is at 700 degrees C. And the amount of heat that it absorbs is 1,000 kilowatts. All right, so remember, we looked up previously that 1 watt is equal to 1 joule per second. Okay, so kilowatt would be 1,000 joules per second. The heat's absorbed, so it's positive. Then we're told that our plant rejects, all right, so we're rejecting 850 kilowatts. So QC would be a negative 850 kilowatts. Okay, so remember watts, joules per second. I have a dot up here, so I have my rate. And we're rejecting heat to a river at 25 degrees C. So TC, let me just move it so I can label it. So TC is 25 degrees C. All right, so then the first question is, what is the efficiency of the cycle? All right, so if I think about efficiency, okay, just like when we tackled our Carnot engines in the past, our efficiency is going to be the desired output over the required input. Okay, so the desired output, right, is, so our desired goal, right, is to produce work. The required input, right, is going to be heat. Okay, so our desired output is the net amount of work produced by our power plant, right? Some of that work produced, right, is being fed and is input into our pump. All right, so think of this as so this is a power plant, right? This is a power generation cycle. All right, so yes, we're producing some work in our turbine, but then we also require some, power to power that pump. So desired output is our net work. Okay, so desired output is work. Now we expect that work term to be negative since it's work done by our system. Right, the net effect of this should be to produce work. So I'm going to label that as a negative W, or I could use an absolute value sign and everything. Either way would be fine. And then my required input is this heat that's required in my boiler. Okay, so my desired output is the net work produced by my system. Okay, and I'll write it as a rate in this case. And then my required input is the heat required in my boiler. Okay, so desired output over required input. All right, so now looking at the problem, we're given QH, okay, but I don't know W. Okay, so this is where we take advantage of the fact that we have a cycle, right? That if I start and end at point 1, that the change in my state functions, so think of enthalpy, internal energy, and entropy, are all 0. Okay, so if I take, all right, this to be my system, okay, and if I think of my first law of balance, so just as before, we're going to ignore, we'll have steady state operation. We'll ignore any effects due to kinetic or potential energy, right? And so for my cycle, my first law of balance reduces to 0 is going to be equal to Q dot H plus Q dot C, I called it, okay, plus I'll label it W dot T and W dot P for now. Okay. Okay. Now here, W dot is just my net work. Okay, so I'm going to group these two work terms together and just call it W dot. Okay, so I'm going to take my first law of balance to be 0 is equal to Q dot H plus Q dot C plus W dot. Right, and the left-hand side, again, we're assuming steady state behavior. We're ignoring any effects due to kinetic or potential energy. So my plant's not moving, and we are we have a cycle, right? So we're starting and ending at the same point. So the change in all of our state properties are going to be 0, right, for our process. All right, so let me add a new page. And so what I'm going to do is I'm going to rearrange and solve for W. Okay. So W dot then will be equal to negative Q dot H minus Q dot C. So then in my efficiency, where I had negative W over Q dot H, that'll be equal to negative, so of a negative quantity, so this will be plus Q dot H plus Q dot C divided by Q dot H, and so that'll be 1 minus Q dot C over Q dot H. All right, so 1 minus, all right, and this is kind of cool. This is the amount of heat rejected over the amount of heat absorbed by our system. Okay, so nice. So computing then, all right, we get, so I'm going to jump over to MATLAB just because, so I can tabulate everything up here. All right, you've got access to my calculator then. So we have QH was 1,000, and that's kilowatts. And QC was equal to negative 850. Okay, and that is also in kilowatts. All right, so now that I look at this, does this make sense? Am I going to have a sign error? Because I have up here negative QH minus QC, which I agree with. And so then this is, oh, it's not a 1 minus, it's a 1 plus. Okay, because it's QH plus QC over QH. My apologies, right? where I was having a mental moment before is if QC is negative and it's 1 minus that term, this would be positive. I'd end up with an efficiency greater than 1. Okay. All right. Problem averted. So we have QH, we have QC. So then my efficiency is going to be equal to 1 minus QC divided by QH. And I just did it again. 1 plus QC divided by QH. All right, and this later term here is negative, so I end up with efficiency less than 1. Okay, good. All right, so I get an efficiency of 0.15. So I have an efficiency of 15%. All right, so not too great. So my efficiency is 0.15. All right, so what's the efficiency of the cycle? There we go. And yeah, while we have it, let's go ahead and let's compute our work. And so let's compute everything, and then we'll go and calculate our entropy generation. Right? Just because we have the information now, let's do it. So eta is 0.15. So if I wanted to solve for W then from here, right, W dot is going to be equal to negative eta times Q dot H. Okay. So therefore, my network, remember this is the network produced by my system. So W is going to be equal to negative efficiency times QH. Negative makes sense because the net effect is for my system to produce work. Okay, so my system's going to produce negative 150 kilowatts. Okay, and it's negative because the net effect is my system is producing work. All right, hence my negative sign. All right, so I have eta, I have W dot, I have QH, I have QC. I can't solve for WT and WT, or WT and WP, because I have W, but I would need to know WT or WP in order to pull out the other one. All right, so then let's move on and let's calculate the rate of entropy generation. Okay, so next I want to calculate SGen. Okay. Now when I go to my entropy balance, right? So just thinking in terms of my first law or thinking about my entropy balance from chapter 4, right? So in the context of chapter 4, okay, because this is what I have in my head. Even when we expand it for open systems, all we need to do is account for flows in and out when we talk about changes in our system. But from chapter 4, we had SGen was equal to delta S of my system, okay, plus delta S of my surroundings. Now, from our analysis of our Carnot cycle back in chapter 4, remember, key is here, just like in chapter 4, we have a cycle, right? A Rankine cycle, just like Carnot, is a cycle. So, okay, I'm sorry I keep emphasizing this, but this is the key for cycles, is that if I perform an analysis on my process, I start and I end at the same point. Okay, so the change in my intensive properties is going to be 0, right? So the change in enthalpy, entropy, internal energy, for this process will all be 0 since I'm starting and ending at the same point. Okay. So it's going to be the delta S of my system is equal to 0. So when it comes to calculating SGen, what I really need to account for is the change in entropy of my surroundings. So let's write this out. So in the context of an open flow problem like this, or a problem here where I have rates, right? I would write this as SGen is equal to, okay, now in terms of my surroundings, what I'm going to assume is if I go up to my plant, I'm exchanging heat in 2 places. Okay, I'm exchanging heat in my boiler and I'm exchanging heat in my condenser. Okay, so what I'm going to assume is that from my this heat that's being absorbed in the boiler, that's coming from a bath, right, at a temperature of 700 degrees C, and I'm going to assume that the heat rejected in my condenser, right, it's also being rejected to a bath, in this case at 25 degrees C. and we definitely get the rejection to a bath, right? It's, we have a river at, 250 degrees C, right? So if the river keeps flowing, I'm sure its change in temperature will be negligible. And if I think about the boiler, right, that's probably coming from some sort of furnace, right, that's going to be maintained at some, constant high temperature. And it tells us furnace. All right, so in terms of my surroundings, okay, what I'm going to have is I'm going to write it as, I'll call it, my Q hot bath over TH, right? It'd be the temperature of my bath, which I call TH, plus, and these are going to be rates. I need my dot up here. So I'm going to have Q dot C, my cold bath, divided by TC. All right, so now in terms of this, right, if I think of my hot bath, okay, the heat that's absorbed by my boiler, which I labeled here as Q dot H, is equal but opposite in sign to the heat of my bath. So the heat that's rejected from my bath is absorbed by my boiler, okay, just like the heat rejected by my condenser is absorbed by my cold bath, okay? So the magnitude will be the same, right? The absolute value of the heat in these two cases will be the same, but we have to change the sign because of our sign convention. Heat's positive when it's absorbed, it's negative when it's rejected. Okay, so I just need to change my sign. So I get S gen would be equal to, so this would be negative, what I've labeled as Q dot H, right? So thinking about heat from the perspective of my boiler, divided by TH, plus Q dot C minus Q dot C over TC. All right, so we know TH, we know TC, I know QH, and I know QC. Now, to calculate my entropy generation, okay, for my temperatures here, again, make sure we're using absolute units of temperature, right? Make sure you're using absolute units of temperature. Okay, so computing, we have QH and QC already over in MATLAB. We need TH and TC. Okay, so TH is going to be equal to, so it's 700 degrees C, and I'm going to add to it 273.15 to get that in Kelvin. TC is at 25 degrees C. I'm going to add to it 273.15 to get that in Kelvin. Okay. So then S gen, okay, so my heats are in kilowatt, so S gen is going to be kilowatt per Kelvin. So S gen is QH divided by negative QH divided by TH minus QC divided by TC. So running, I get an entropy generation of, so it's positive, so that's good. All right, that's how it should be. Positive 1.8233. So S gen is a positive 1.8233. And that's going to be kilowatts per Kelvin. Okay, remember a watt is a joule per second. So you can think of this as kilojoules per second Kelvin. Okay, per second because it's a rate. All right, so there's S gen. We solved for efficiency. We even calculated the net work produced. Okay. And now in C, it says, what is the maximum possible power that could be produced by a plant given the temperatures of the furnace and the river? What is the maximum possible power that could be produced by a plant given the temperatures of the furnace and the river? Okay, so we're not given T. So assuming we have, we want the maximum possible power, right? So the maximum value of W. Okay, so we're not necessarily given QH and QC here, but instead we're given TH and TC. All right, so we've got to go back to our friend Carnot and think about this from a Carnot perspective. Okay, and so what we're going to find is that the maximum amount of work produced is going to happen when Sgen is equal to 0. All right, so when we have a reversible process, when the entropy generation is 0, that's when the net work produced is going to be a max. Okay, so if I go to my Sgen equation here, right, it'd still be the same. I have a cycle, so I'm still going to have the delta S of my system is 0. So what I'm going to end up with is this equation here. Okay, so again, delta S of system is going to be 0 because I have a cycle. And so, I'm still going to have heat exchanges as I have them labeled in my picture. I just don't know what their values are. Okay, so I'm going to have Sgen is equal to 0 for this maximum case, where S dot gen is equal to negative Q dot H over TH minus Q dot C over TC. Okay, and that's going to be equal to 0. So what I end up with is, let's see, so I have Q dot H over TH is equal to, it doesn't matter, I put the negative Q dot C over TC. Now before I manipulate this any further, what I want to do is I'm going to go back to my efficiency equation and then my first law balance. Both of these will also be exactly the same. So I'm going to go back to both of these and see how I could use that Sgen equals 0, my entropy balance equation, to simplify this to get it just in terms of temperatures. Okay, so let me add a new page. Okay, so I have the QH over TH is equal to negative QC over TC. From our first law of balance, we had that 0 was equal to Q dot H plus Q dot C plus W dot being my network. And what we're trying to get to is we're trying to get to my efficiency, which is equal to negative W dot over Q dot H. Okay, so how I'm going to get there is actually I'll do exactly what I did before. Okay, so if I were to solve this for W, I end up with W dot is equal to negative Q dot H minus Q dot C. Okay, so plugging that in here, we end up with eta is equal to, so negative of both these are negative, we get Q dot H plus Q dot C over Q dot H, and so that's going to be equal to 1 plus Q dot C over Q dot H. Okay, so what I need is Q dot C over Q dot H. Okay, got it. So from here then, so Q dot C over Q dot H. Okay, so solving, well, so if I multiply both sides by 1 over QH and then by TC, I end up with negative TC over TH is equal to Q dot C over Q dot H. Okay. So going back to here, this then would be equal to 1 minus TC over TH. Okay. And this makes sense. It's negative now because TC and TH are my temperatures in absolute units, so they'll both be positive, where TC is greater than TH. So my maximum possible efficiency, I already have everything, so my maximum efficiency will be equal to 1 minus TC divided by TH. So the maximum efficiency is 0.6936. Okay, and so this will be my max efficiency. So my max efficiency is about 69%. All right, my plant's only operating at about 15%. All right, so it doesn't seem like our plant is operating close to the optimal value. And yeah, so that's the last question. What's the maximum possible power that could be produced? Um, well, what's the maximum possible power that could be produced by a plant given the temperatures of the furnace and the river? Oh, okay. So we have the efficiency, but they want the maximum power. Let's see. So now we have my maximum power, but we're not given QH or QC. We're only given those temperatures. Well, so in order to find that maximum possible, right? So if that's eta max, okay, if I go back to my definition of my efficiency, okay, what I'm going to get is that W dot max, right? If I come back up here, W dot max will be negative eta times Q dot H. All right, so it tells me, what's the max? So the energy that I'm putting in the form of heat, what's the most that I can get out as work? All right, so it'd be calculated as such. So as I think about this problem, right, I had interpreted C as we didn't know what QH and QC was. But how I'm going to interpret this is if they want to know the maximum power of work, we either need to know QH or QC, or say what that actual maximum W is, right, in order to be able to solve for the others based on the information provided. So what I'm going to assume is that we have still an input of 1,000 kilowatts coming from our boiler. So I'm going to assume that Q dot H is still 1,000. Okay, so that if I want a W max, it's going to be this negative efficiency max times QH. Right, I'll assume that I'm still, receiving heat from that same source, and so that max would be negative 693. All right, so my maximum work would be a negative 693.6238. And that's going to be kilowatts. All right, so I hope that helps. If you have any questions, by all means, please let me know.